Yeah, good evening guys. So welcome back. I hope the audio and video is fine, right? 𝐂𝐨𝐿𝐻𝐿, hi Krishnan, every one of you, kids gaming. So please do type in the chat box. Is the audio and video clear to all of you? Yes? There was slight issue in the chat, right? I think there's a delay, lag. Is the audio and video clear to all of you? Please type in the chat box. No? Yes? Yeah, so please, it's clear, right? Okay. Thank you. The audio and video is clear. Great. Okay, so we'll start the session, of course. So we are again continuing with the 7 p.m. series. Okay, we have started engineering mathematics in English, of course, a week back, and in the last week completely we have started looking at linear algebra in some much understandable sense. Okay, so I think even many of you might have seen the definition. We have started straight away from the definition of matrix, and then after we started learning so many things about the concept of rank, the consistency in case of linear systems. Okay, then after, what does an eigenvalue do actually? Okay, and how would we calculate eigenvalues, and of course we'll also see how we calculate eigenvectors in much detailed sense. But in last session, or till last sessions, we have talked about the eigenvalues in much detail. So today is lecture number 7 of this linear algebra. So in this lecture, basically we are going to talk about eigenvectors and diagonalization, and along with that we'll also see the linear combinations, linear dependency and independency, and we'll also, if time permits, we'll also go for slight iterative methods, which is decompositions. Okay, LU and SVD, singular value decompositions, because SVDs are very predominant in data science courses exclusively. So we are going to deal these things. Okay, and coming quickly to the channels, of course. So every update on this YouTube channel is posted in this Telegram channel. So if you just scan this, it will direct you to the Telegram channel, which leads to the updates of this channel. Okay, so I basically suggest you to all of you to scan this and get in touch with this channel so that you don't miss any content. Okay, and this is my personal group maintained by me and my students of PW. So you can, if you want to get some guidance, or if you want to get in touch, or if you want to know better anything, you can just scan to this group. And also I suggest you to install this Unity, and of course if you have this, you will have all the track of your doubts and notes at one singular place. Okay, so that definitely keeps you intact with all the subjects. Okay, so let's say for example throughout till GATE 2025, you have attended so many YouTube sessions, and you have done a lot many polls, and you have also done so many what we would say like you have asked so many doubts. Okay, so in all these cases it keeps a track record, it maintains a track at one particular point, of course. Okay, so coming quickly, so before you type the doubt, you can type exclamation doubt, and then you can start typing your doubt so that it directly stores it at that point. And also exclamation notes could save it again in the notes tab, of course. So coming to the last lecture, so in the last lecture we were mainly talking about eigenvalues. So if you have any vector x, and if this matrix, when you transform on this vector, is changing only its length but not its direction, then we say that's an eigenvector. And from this we have come up to the solution a minus lambda I operating on x is equal to 0, of course. Okay, or yeah, of course it gives you a vector, so a minus lambda I into x is equal to 0. And here you can see this coefficient should have the determinant 0. This implies for non 0, or that means for x not equal to 0, if this has to have a non-trivial solution, determinant of a minus lambda I is equal to 0. That's what we have seen, and we have seen certain techniques in order to solve these characteristic equations. Okay, so this is basically called the characteristic equation that talks about characteristic equation that talks about the eigenvalues, of course. Okay, so these are the things that we have seen in a much broader sense in the last lecture. So we talked about eigenvalues of different types of vectors. So eigenvalues don't depend upon the vectors. No, it depends on the matrix actually. Okay, and eigenvalue tells you basically to what length a vector can be stretched or shortened. This is what it comes up. Okay, so how many marks will be coming from linear algebra? Normally if you look at the previous papers, it's like around 3 marks. Clear? Now let's see. We have given some questions as homework. Of course, in the last lecture we did not solve this question. So you can see if you solve this. Oh, just a minute. Just give me a minute, of course. So there was a poll which I accidentally has missed it today. So let's see. this unity is what I suggest you, of course. So you all have to have this. And so in this question, basically in this particular question, we have calculated the value of x. Okay, so and if some of you have solved, you please enter the answer in the poll. The value of x for the matrix so and so matrix has 0 as one of the eigenvalues. Okay, so if this matrix has 0 as one of the eigenvalue, then you think what value of x should be there such that it actually fits 0 determinant. Come on, if you have solved this question, please enter the answer. Hi Krishnan, did you get the idea? Basically lambda tells you to what length or to by what factor the vector gets stretched or it gets compressed. Okay, it doesn't perform any rotation, and this eigenvectors and eigenvalues lambda and xa are a pair which are bonded together. Okay, it's not like they are different, but every lambda has a particular xi. Clear? So let's see. So anyway, let's see if this matrix has to have 0 as an eigenvalue. If x has to, if A has to have 0 as an eigenvalue, if this has to have 0 as an eigenvalue, then that determinant of A has to be 0, of course, correct? Now if that A has to be 0, then definitely you can calculate the determinant and take it to be 0. But you can understand one point here. If you slightly observe, this 3 and this is -6, this is 2 and this is -4. So ultimately if this -9 plus x is equal to -8, then ultimately this implies R3 is equal to 2 times of or -2 times of R1, of course, correct? And if these two rows are proportional, then ultimately determinant is going to be 0. So clearly if you can make this -8, for example, okay, because this is -6 which is -2 times of 3, this is -4 which is -2 times of 2. So if you can somehow make this -9 plus x to be -8, then ultimately third row becomes -2 times of the first row, and ultimately determinant is going to be 0. So therefore -9 plus x is equal to -8, so x is equal to 1. That's all. Clear? That's it. So of course I know many of you might have solved the determinant and equated it to 0, but still you got 1, because if you just observe the determinants for a slight time, okay, then you can figure out few things like this. Got it? I know majority of you might have solved this determinant and equated to 0, so that then you got x equal to 1, of course, but this is also a simple technique to understand this x is equal to 1. Clear to all of you? Hari Krishnan, Banu, Sagnika, Thomas, Shreya, every one of you, Kids Gaming, Ashwini Kumar Biswal, everyone. In fact, I could read only these names because the chart is only up to this. Is this clear? So what will be the other eigenvalues then? If 0 is one of the eigenvalue, then let 0 is one eigenvalue. So 0, lambda 2, lambda 3 are eigenvalues. Okay, are eigenvalues, of course. So you can calculate lambda 2 plus lambda 3 is equal to how much? Lambda 2 plus lambda 3 is equal to 3 plus 7, 10. 10 minus 8, 2. Okay, so because 1 is 0, so lambda 2 plus lambda 3 is equal to 2. This is one equation. Then how to get the other equation? I've told you a technique in order to get this value. I've told lambda 1 lambda 2 plus lambda 2 lambda 3 plus lambda 3 lambda 1. This is going to be equal to sum of the principal minors, correct? So if you take, for example, this element as -8, and if you take the sum of principal minors, you will get some number. But you also know one thing, this term is 0 because lambda 1 is 0. This lambda 1 is also 0, so you'll also get lambda 2 into lambda 3 is equal to something. Then you have lambda 2 plus lambda 3 equal to 2, and lambda 2 into lambda 3 is equal to some number. If you solve, you'll get lambda 2 and lambda 3. Got it? That's how you can calculate eigenvalues, all three eigenvalues, of course. Clear? One is 0 and the other two lies depending on these two equations. Clear? And this is equal to sum of principal minors, which we have seen, of course, the other day. Sum of principal minors is what you're going to get. Okay, now let's go to the, so ultimately the answer is going to be 1, of course, and I think, yeah, 100% of you. Sagnika, within time I think you have marked, and Banu, yeah, you're also right. Now let's go to the next question quickly. Chalo, I gave you as homework, so what's the answer you have got? Integer type. Again 30 seconds. If you have solved, please enter the answer. If this is the matrix whose eigenvectors correspond to lambda 1 and lambda 2 are, so x1 is the eigenvector corresponding to lambda 1, x2 is the eigenvector corresponding to lambda 2, x1 transpose into x2 is dash. Come on, enter the answer quickly. Of course, you know, if you know one property, it could be much better, but anyway, we'll see. Sagnika is typing 0, others nothing. Chalo, let's see. if you solve this, consider the matrix A is equal to 50, 70, 70, 80, whose eigenvectors corresponds to lambda 1 x1, which means basically A x1 is equal to lambda 1 x1 and A x2 is equal to lambda 2 x2. This is what they mean, okay, where x1 x2 are these vectors. So x1 transpose into x2, so x1 transpose into x2, this is what we have, okay. Lambda 1 is the eigenvalue and lambda 2 is also another, oh sorry, this is lambda 2 I think, okay, sorry, this is lambda 2, it's a typo, so lambda 2 minus 80. Now let's see if that's lambda 2. I think many of you will be able to solve now. Yeah, correct, Gauthami, 0. Now if you multiply x1 transpose into x2, you will get 70 lambda 1 minus 50, this is x1 transpose multiplied with lambda 2 minus 80 and 70, that's what we have, clear. So this is of size 1 by 2 and this is of size 2 by 1, so ultimately if you multiply you will get a scalar, okay. So let's see what is the scalar. 70 times lambda 2 minus 80 plus lambda 1 minus 50 times 70, this is what you get, correct. So this is the term what you have, of course. Now if you simplify this, you can see 70 times lambda 2 plus lambda 1 times 70, which means 70 times of lambda 1 plus lambda 2 is what you will have. Then minus 80 into 70 minus 50 into 70, so minus 70 into 80 plus 50, total 130 is what you get. Then what is lambda 1 plus lambda 2? You have the matrix. So if you want lambda 1 plus lambda 2, sum of eigenvalues, sum of the principal diagonal elements, which is 50 plus 80, which is of course 130. So 70 times 130 minus 70 times 130, of course. So clearly these two cancel up and you will have zeros, right? So this is 0. And of course after some time I'll teach you one important point. If you take any symmetric matrix, okay, of course when we come to the discussion of eigenvectors, which we didn't go at detailedly, but we'll go into this class. So if you just talk about the eigenvectors of a symmetric matrix, the eigenvectors of symmetric matrix are pairwise orthogonal. Means if you take any two eigenvectors and if you do dot product, you'll definitely end up with 0, okay. It's because of the symmetricity in the matrix. We'll see how that comes up. So but this question, we even without knowing that point, you can just do a simple 2-3 steps so to find the answer to be 0. And all of you, Gauthami, Ajay, yeah, all of you are correct actually. So 0 and nice, okay, again Saknika, good. So if you see the poll, I think Saknika is the only participant, fine. So let's go to today's class. So in today's class the major discussion will be on eigenvectors and diagonalization. This is really a very beautiful concept which people use many times, because times when even if you have the systems like this, Ax is equal to B, okay, and if you want to solve this, and you know when generally when this matrix is singular, okay, if that determinant of A is equal to 0, this system cannot be solved directly, okay. X is equal to A inverse B, of course, but this is not possible, okay. This A inverse you cannot calculate. So in situations where you have this A inverse not existing, or basically A is singular, then in such cases we can jump to the diagonalization concept. Diagonalization can help you solving that equations, okay. We'll see how these things happen. So and also iterative methods along with linear combinations I'm going to teach. Basically linearly dependent and linearly independent vectors is what we are going to look today, and we are going to connect these linear combinations to vectors so that it could benefit us, okay. And chalo, let's start with eigenvectors and diagonalization. So first of all let us start with eigenvectors a bit. Eigenvectors. So clearly you know a vector x corresponding to, of course, x non-zero, x is non-zero, clearly x is non-zero corresponding to an eigenvalue lambda, corresponding to an eigenvalue lambda is given by Ax is equal to lambda x, the equation which satisfies this, you know this, okay. So we have seen, or basically we will see how to calculate the eigenvectors. So like any of the equations has two eigenvalues, right, since it's 2 by 2. Sorry, didn't get you, sir, one doubt. Like any of these equations has two eigenvalues, right, since it's 2 by 2. Yeah, basically if it's a 2 by 2 matrix, then we'll have two eigenvalues because the characteristic polynomial will be of second degree, okay. So get back here to this point. Ax is equal to lambda x, okay. And how to calculate an eigenvector first of all, basically, okay. So let's say I have given you some matrix, then how to calculate an eigenvector we'll show you, okay. So let's see example. A is equal to, like the same matrix I'll take 4 2 2 2 4 2 and 2 2 4, because this matrix has a specialty, its determinant is clearly you know not the determinant, sorry, it has some symmetricity in the rows. Okay, it's a symmetric matrix, of course, and we'll talk about some nice points which make you understand things. Okay, basically whenever all the 3 eigenvalues are different, you can easily calculate eigenvectors and all. But when two eigenvalues are, one of the eigenvalues is repeating, okay, then how to calculate the eigenvectors, how you get 2 different eigenvectors for the same eigenvalue, these kind of things can be easily understood if I start working with this matrix. So intentionally I'm starting with this matrix, because for a normal matrix where you get 3 distinct eigenvalues, you can easily calculate eigenvectors. Okay, but for this I want to show you something different. Look, for example, I just want to show you eigenvectors of this matrix. Okay, then if you calculate, in the last class we have calculated this, we got the eigenvalues to be 8, 2 and 2. Okay, so you can see we have done it in the last lecture. So this eigenvalues we have calculated, that of a minus lambda equal to 0. If you simplify, we got lambda 1 equal to 8, lambda 2 equal to 2, and lambda 3 is also equal to 2. Now first let us calculate the eigenvector corresponding to lambda 1 equal to 8. Okay, so eigenvector corresponding to lambda 1 is equal to 8, of course. Okay, so if you do that, ultimately you know ax should be equal to 8 times of x. So this tells you, so if you multiply a with x, let x is equal to, initially you don't know what is the eigenvector, so you take maybe x1, x2, x3 are the components of this vector. We are dealing in 3-dimensional space, so we are taking 3 components to represent a vector. So a into x could give me something like 4x1 plus 2x2 plus 2x3, then we can get again 2x1, 4x2, 2x3, then 2x1, 2x2, 4x3. This guy is equal to 8x1, 8x2, 8x3, of course. Okay, so this is what you get. Or in general, you can also see, if you simplify these equations to a homogeneous system, x2 plus x3 minus 4x1 plus x2 plus x3 is equal to 0. Okay, so minus 4, okay, this is minus 2 then in this case, because if you cancel 2 all over, minus 2. Okay, so this is what you get, because if you cancel 2 on all the sides, it's like 2x1, it's like 4x1, so 2x1 minus 4x1 gives you minus 2x1, of course. Okay, and you have x1 minus 2x2 plus x3 is equal to 0, x1 plus x2 minus 2x3 is equal to 0. It's a homogeneous system, and if you solve these equations, for example, this equations if you solve, you will get x1 is equal to x2 is equal to x3. Okay, you know how to solve the equations with the unknowns, you can solve directly. So if you just solve, you will get x1 is equal to x2 is equal to x3 in this case, because you can see if you put x2 equal to x3, that fits all this system. Okay, so therefore x is equal to x1, x2, x3. So if you replace this, you will have x1, 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 and if you take x1 common, you will have the vector 1, 1, 1. Clear? So this is a vector 1, 1, 1, and you can understand few points here. This x1 can be any scalar, it doesn't matter, and the eigenvector corresponding to lambda equal to 8, corresponding to, of course, in today's class we'll go in much detailed sense how to solve this system of equations, but of course it's like a 3 equations 3 unknown, so everyone knows how to solve this. So this is what you'll get. So eigenvector corresponding to lambda equal to 8 is 1, 1, 1 actually. Okay, so this is how you get an eigenvector. Of course, whenever you have these equations, you can solve and you can get this. So using characteristic equation, how to find eigenvectors based on given eigenvalue using characteristic equation. Basically you can see, I'll just tell you, just a minute. The reason, okay, we'll see something called Cayley-Hamilton theorem, then I'll explain Ajay. Okay, maybe just in some next 40 minutes I'll talk about it. Okay, so see here, this is 1, 1, 1, of course that's what you'll get. Now the eigenvector corresponding to lambda equal to 2, let's see, eigenvector corresponding to lambda equal to 2, of course. Okay, so lambda equal to 2. Now when eigenvector is not repeating, of course this is the process, 8 is coming only once, so this is how you'll directly calculate the eigenvalues, of course. Okay, now whenever this is repeating, how do you do? Let's check. Ax is equal to 2x, of course, and this implies, because eigenvalue is 2, so Ax is equal to lambda x. So if you simplify, you will get 4x1, because 4, 2, 2 is what we have taken, 2x2 plus 2x3, then 2x1 plus 4x2 plus 2x3, 2x1 plus 4 no, 2x2 plus 4x3, this is going to be a 2x1, 2x2, 2x3, of course, right? This is 2x1, 2x2 and 2x3 because this is 2x. Now if you simplify this equation, okay, if you now we concentrate on vector, yeah, of course we are focusing on eigenvectors. Now if you simplify this equation, for example, this first column element should be equal to this element. So if it comes to the left hand side, you have x1 plus x2 plus x3 is equal to 0, right? So you can see, if you solve this equation, for example, 2x1 plus 2x2 plus 2x3 is equal to this is equal to 0, of course. So let's write individually. Maybe 2x3 is equal to 0, and you can observe one thing. If you simplify this equation, second equation, for example, you will get the same thing. Yes or no? 2x1, this 2x2 will actually make this 2x2, and this 2x3 is equal to 0. Similarly, the third equation will also end up with the same equation. Means if you solve any of these equations, you will again end up with the same equation, correct? So that means you can see x1 is equal to minus x2 minus x3, correct? This is what you have. So any vector of the form where the first element is equal to negative of the sum of other two will definitely satisfy this particular equation. Yes or no? That's what this clears us. 2. If you take any vector such that x1 equal to minus of x2 plus x3, then definitely that particular any vector of that particular form would definitely satisfy this equation. That's what this analysis is telling you, correct? Yes, everyone, please type in the chat box. Dipankar, Banu, Harikrishan, Ajay, Gautami, Sagnika, all of you basically. Yeah, 2. Satish, correct? Yeah, that's what it tells us. Now if you want to write an eigenvector, how do you write that? That's the question. So my x, therefore x is equal to x1, x2, x3. So my x1 is nothing but x2 minus x3, x2, x3. This is what you get, right? This is what you get. Now this is like having a combination. If you slightly tick here, we can get something like minus x2, x2, 0 plus minus x3, 0, x3. Can I do this? Yes or no? Because this matrix is same as sum of these two, right? It's like the matrix separation, of course. Okay, we have to do the separation because it's repeating ultimately. So whenever it's repeating, ultimately it gives some of the case like this. So minus x2, x2, 0 and minus x3, 0, x3. So from here, if you take x2 common, you will have the element minus 1, 1, 0 plus x3 if you take common minus 1, 0, 1. That means eigenvectors, therefore eigenvectors corresponding to lambda equal to 2 is r minus 1, 1, 0 minus 1, 0, 1, of course. Okay, so this is what you're getting. 2, correct? Yes or no? Please type in the chat box. Is this clear to all of you? Now I've told you one point. So it means there are two linearly independent solutions. Yes, of course. Okay, these two are linearly independent. Whatever you do, you cannot express this as combination of this. Okay, we'll again come back what is linear combinations and all in today's lecture. But at the nutshell, you can understand this eigenvectors of lambda equal to 2 can be written in this way. Okay, now if you take eigenvectors of any two distinct eigenvalues, okay, I'm telling again distinct eigenvalues. Like for example, if you do the dot product of these two, it's not 0, it will come 1 definitely. You can see if you do the dot product of this minus 1 into minus 1 plus 1, then 1 into 0, 0 into 1, it is 0. But if you do the dot product of eigenvectors of two different eigenvalues, like for example, you take this and you take this 1, 1, 1. Okay, if you do the dot product of this 1, 1, 1 with any of these two vectors, definitely you'll get 0. You can try, okay, because one element one will multiply with this minus 1, it will be minus 1. The second one will multiply with plus 1, it gives you plus 1, minus 1 plus 1, 0. Okay, since it's a symmetric matrix, these kind of things happen. So that's why intentionally I have taken a matrix where you'll get a repeated eigenvalue, and you should know how to calculate eigenvectors when the eigenvalue is getting repeated. Clear? So that's why I have given you this idea. Okay, now let's see. It's okay, Prakasam, just follow up the things. Now let's see, therefore eigenvectors of A are, you can pick 1, 1, 1, minus 1, 0, 1, 1, minus 1, 1, 0. Okay, so these are the eigenvectors of this matrix. Okay, so these are the three eigenvectors. Now let's see. So you know how to calculate eigenvectors even if eigenvalue is repeating. If eigenvalue is not repeating, like how we have calculated for lambda equal to 8, similarly you will calculate, you will get the eigenvector. Okay, now let's see some properties of eigenvectors which help you. Properties of eigenvectors, of course. Okay, so let's see. First thing, the eigenvectors of A and A transpose are not same. Okay, so it's not same. Clear? This is not same. In fact, the determinant is same. You will get the same eigenvalues, but eigenvectors will not be same. Okay, because the reason for that, see, I'll just tell you one thing. If you have A, B, C, D, you have x1, x2. So let's say lambda 1 is one of the eigenvalue. So lambda 1 x1 plus lambda 1 x2. This is what you get. Okay. Now this equation, if possible, can you make it a bit slow? A little bit tough to catch on. Okay, I'm going fast now. Okay, fine. I'll go slow. So see here, if for example this is a matrix A, okay, and this is my eigenvector, and let's say lambda 1 is one of the eigenvalue, for example. Now if you multiply these things, you will get some linear equations. Maybe something like A minus lambda 1 into x1 plus b x2 is equal to 0. Then maybe c x1 plus d minus lambda 1 times x2 is equal to 0. So you got this equation. Fine. Okay, and ultimately when you solve this equation, you will get x1, x2 values. So you can form what is the eigenvector. Now let's say if I transpose this matrix, ultimately this becomes C and this becomes B. C and B, this is transpose. In this case, these equations become A minus lambda 1 x1 plus C x2 is equal to 0 and B x1 plus D minus lambda 2 x2 is equal to 0. If B and C are not equal, okay, so can you please do Li, Ld in case of vectors? Of course, we'll see linearly independent and linearly dependent in today's class. Okay, just maybe, yeah, after eigenvectors I'll teach you. After diagonalization I'll teach you. Okay, just wait for just some 20-25 minutes sort of thing. We'll move. Now let's see. Now you can observe this is the system that you got for Ax is equal to lambda 1x, and you know eigenvalues of A and A transpose are same. So this is corresponding to A transpose x is equal to lambda 1x. Now you can observe one thing. When I have transposed the matrix, these equations got changed. Yes or no? If B is not equal to C, then ultimately these are two different set of equations which may not have the same solution. Understood? Clear? For the same eigenvalue lambda 1, they are giving two different systems, and obviously if you solve two different systems, you will get two different solutions. Clear? So that's why both these equations do not give you the same solution. So that means the eigenvector is not same in both these cases. Got it? It happens only in case of symmetric, because in symmetric A transpose is equal to A, so it doesn't affect, okay, even if you take the transpose. Clear? So can we say matrix A is coordinate system in which the vector x is represented? It's not matrix A, it's basically the vector. Clear? Now let's see, this is not same. Okay, so the reason is, since A minus lambda I into x equal to 0 and A transpose minus lambda I into x equal to 0 are two different systems. Of course. Okay, are two different systems. Then you can see one important point again. The eigenvalues of eigenvectors, we are talking about vectors. So the eigenvectors of A and A power m are same. Like I have explained you in the last lecture at some points, Ax is equal to lambda x is what you will get. Okay. Now since if you go for higher power, so in orthogonal is it same? Yeah. No, in orthogonal also it's not same, because A transpose is equal to A inverse. Okay, but not A again. Okay, that's why. So let's see, if you have this, then if I multiply A, for example, A times lambda x, and this can be written as lambda times Ax, and since x is eigenvector of A, this can be written as lambda into lambda x again. Okay, since A is again eigenvector, so this ultimately gives you A square x is equal to lambda square x. This ultimately tells you that lambda square is eigenvalue of a square, and this x here eigenvector of x square, sorry, eigenvector of a square. So even if you do it one more time, a cube x is equal to lambda cube x is what you will get. So that tells you this vector lambda, this vector x do not change with raise of power of x actually, sorry, raise of power of a. Okay, so therefore this x remains same either for a square, a cube, whatever the power you take, that remains same. Okay, so eigenvectors of a and a power m are same. Third, eigenvectors of a real eigenvectors of distinct eigenvalues of a real symmetric matrix, are mutually orthogonal, or you can write pairwise orthogonal. This point is very important. Pairwise orthogonal actually. Pairwise orthogonal. So what does this word pairwise orthogonal tells you? Now let's say for example if I take a matrix, then I can generate a number of eigenvectors. Now whenever I have eigenvectors xi transpose dot xj, if I take the dot product of two vectors, okay, or basically if I do dot product, simply instead of matrix form I just represent normally xi dot xj is equal to 0 for all I not equal to j. Okay, means if you take any two different eigenvectors and if you make a dot product, you will get 0. Like for example, you can see we have solved one question. In this explanation, what we have seen, this is a symmetric matrix. Okay, so you can see this is a symmetric matrix 50, 70, 70, 80. So these two elements are equal. Now if you see this x1 is one eigenvector and x2 is another eigenvector, if you do the dot product of these two, ultimately you will get 0, which you have seen of course. Okay, so the eigenvectors of a real symmetric matrix will be orthogonal, pairwise orthogonal of course. Okay, now let's see, let's go into the concept of linearly dependent and independent. Okay, so linear combination of vectors. Linear combination of vectors. This is important actually. It's in ECE, TEPLI and in data science also of course. Okay, so linear combination of vectors. This is pretty much important concept to be frank. Now even in general mathematics it holds a very good role. So when we are fixing matrix, we are actually trying to find a vector which doesn't rotate and just touches, right? Yeah, of course, that's what the eigenvector I have told you. So when fixing matrix, both eigenvalue and eigenvector is unknown, right sir? Yes, but they are connected to each other. Clear? Okay, we are not finding matrix. Okay, so for one way we are doing is we are actually finding vectors. If we have a matrix, we are identifying is there any direction in which the vector will not actually rotate. Okay, it just gets stretched. That's what we are finding. Okay, physically. Understood? Let's say I have three-dimensional space. Okay, if I have three-dimensional space, then is there any direction along which this matrix can actually perform only stretching or shortening but not rotation? That's what we are finding. Done? Now let's see here linear combination of vectors. So of course we have taught, I thought of teaching you vector spaces also, but anyhow we'll put that to the last because it's just a basic concept. So let's see, normally if you have linear combination of vectors, let x1 x2 and so on xn are n vectors, and alpha 1, alpha 2 and so on alpha n are n scalars, then the combination sigma I equal to 1 to n alpha I xi is called linear combination of vectors, because we have combined the vectors linearly. Linear combination of vectors actually. Okay, so obviously if you expand this, just if you expand the summation, summation I equal to 1 to n alpha I xi, this tells you alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3 and so on plus alpha n xn. This is what we have the linear combination. Okay, now what is this linearly dependent and what is linearly independent? Okay, so that's the main important idea. Now let's see linear dependence. Okay, linear dependence of vectors. Linear dependence or linearly dependent, you can say, of vectors, linear dependence of vectors. If summation I equal to 1 to n alpha I xi is equal to 0 such that alpha 1, alpha 2 and so on alpha n all are not 0 at the same time, not 0 at once, then the combination is said to be linearly dependent. Linearly dependent. Okay, so these are linearly dependent, they are not zeros. Okay, they are said to be linearly dependent. Alpha, it's not equal to 0, right? So really what the matrix will represent, basically forming of elements in a particular order, that's it. Yeah, in independent of course. Okay, so first we are talking about linearly dependent. Look, for simplicity I'll explain you using a 3-dimensional space. Okay, so vector has 3 components. We'll look at this. See here, example, let's say I have vectors x1 is equal to say 1 2 3 for example, x2 is equal to 2 4 6, x3 is equal to say for example -1 0 2 something like this. Okay, so let's say you have these vectors. Then if I want to say whether these vectors are linearly dependent or independent, okay, then what I can do is first of all form the combination. Okay, so linear combination, first of all let's write linear combination. So if you look at this linear combination, see what happens. Alpha 1 times 1 2 3 plus alpha 2 times 2 4 6 plus alpha 3 times -1 0 2 of course. Okay, so let's say this is the combination. Now let us check whether it is linearly dependent or not. Okay, for linear dependence what I told is this summation should be equal to 0 such that all these are not 0 at the same time. Okay, maybe one can be 0 and others few cannot be 0 like that, but not all are 0 at the same time. Now say alpha 1 is equal to 1 or alpha 1 is equal to 2 for example, alpha 2 is equal to -1 and alpha 3 can be 0, let's say. Okay, so alpha 3 is equal to 0. So let's say we have some values of scalars such that this combination is 0 but all these scalars are not 0 at the same time. Okay, so you can see alpha 1 is 2 and alpha 2 is -1 of course. Then ultimately you can see the given vectors are such that we have 2x1 plus x2, sorry minus x2 of course, because plus -1 into x2 plus 0 into x3 is equal to 0 of course. Okay, so you can see this is a combination what we have. Now in this combination sigma alpha xi is equal to 0 but all alphas are not 0 at the same time. So we can say that this combination is linearly dependent. Means if you take any vector you can say x2 can be written as -2x1. This dependency concept is not very new to you. Like for example, if you take an equation y equal to mx, then you can see this x is a variable and this y is called the dependent variable. Why? This y is actually depending on this x. Similarly here, one vector will depend on the another vectors. That's it. Okay, we can write a linear combination like this if these vectors are linearly dependent. Okay, x2 equal to -2x1 I can write only if all these are not 0 at the same time. Then we can say x2 is depending on x1. That's why this combination is said to be linearly dependent combination. Clear to all of you? Yes or no? Please type in the chat box. Faster a bit. Okay, yes or no? Please type in the chat box. Is this clear to all of you? Did you understand why we are telling it linearly dependent? Because it's a linear combination ultimately, and here few vectors are depending on the linear combination of other vectors. That's why it's a linearly dependent combination. Got it? Everyone should type in the chat box. If you have some issue at any point, please ask me. I'll be able to clear that, because it's really an important concept, okay, as we move forward. Of course, not to the level of this class, at least in the GATE syllabus level, but beyond, in your future, if you start working on data science or things beyond that, then linear combinations are really something which is important, okay, you should start worrying about. Fine. Now let's see, if this x2 is equal to minus 2 times of x1, okay, then this tells you therefore x2 is linearly dependent on x1 and x3 also. Maybe you can say 0 into x3, it doesn't matter, 0, because all are not 0, so you can say 0 into x3. Now if I give you any set of vectors, for example, how do you identify whether they are linearly dependent or linearly independent? That's the main crux, okay, because it's not like, see here, since I have explained you by taking alpha 1 equal to 2 and alpha 2 equal to -1, you are happy, you have understood everything. But let's say if I just give you some 3 random vectors, and if I ask you whether they are linearly dependent or linearly independent, okay, then how would you understand? Let's see how to identify a given set of vectors. Of course, in 3D we are talking. You can extend this to any dimensions, maybe n dimensions. How to identify a given set of vectors, are linearly independent or linearly dependent, okay, are linearly dependent. This is the main question. So let's see, okay, so is it possible that solution also linear combination of vectors? We'll see, okay, what's the solution will come close, okay, but as of now, look at this. So how to identify a given set of, in fact I'll teach you the linearity in differential equations, okay, linear, whenever you have differential equations which are linear, and if you can club them, then ultimately you can just add their solutions. We'll see this principle of superposition in differential equations, but right now let's limit ourselves to the vectors, okay. Now if I give you these vectors, say x1, x2 and so on xn are n vectors in n dimensional space, let's say are n vectors, for example, then you can understand something. If let x1 is equal to, x1 has got the components like maybe say alpha 1, no, okay, alpha will eliminate because we'll use for constants again. So let's say a1, b1, c1 and so on, let's say n1 maybe, let's say, okay. So this is a vector, means these are the components in n dimensional space. X2 is equal to a2, b2, c2 and so on, maybe some n2, and of course this I'm assuming to be n, okay, so that you have, see, ABCDs, if you count in order up to n, you'll get maximum A B C D E F G H I J K L M N, you'll get only 14, okay, but my intention is maybe you're putting some numbers in between so that you're having total n elements in the space, okay, then and so on. Let's say xn is equal to an, bn, cn and so on, of course till nn, let's say, okay, yeah, nn, okay, this is what you get. Now if I represent this in a matrix, for example, okay, so if I represent this in a matrix, let A is equal to x1, x2 and so on xn, such that this x1 is actually nothing but the column matrix which contains a1, b1, c1 and so on n1, of course, okay. So that's how the size of this matrix is actually n by n. Clear? Did you understand? See, basically, yeah, it's n dimensional space, okay, I'm just generalizing things so that you can work in 3 dimensional space, but in general if you work in n dimensional space, how you get the things. So when you have this n vectors, what I suggest you is you put a matrix such that A is equal to x1, x2 and so on till xn, such that each vector in this, let's say for example if I get x1, that actually represents this column, so that you have first column, second column, third column and similarly nth column. That's how this matrix A is n by n matrix. Clear to all of you? Did you understand? This vector x1 is a column vector which maybe transpose, okay, so you put transpose here so that it doesn't matter, it's a column matrix. It's a n by n matrix, right? Yes or no? Clear to all of you? I'm framing a n by n matrix using these elements. That's it. Okay, such that each column is one vector. That's it. Okay, each column is a vector, so that I have total n vectors, and each vector has n components. So ultimately, the matrix generates a n by n matrix. Okay. Now let's see if vectors are linearly dependent. For example, if vectors are linearly dependent. Linearly dependent. Okay, if vectors are linearly dependent, that means, let's say for example you take the vector xm. Okay, so let's say let xm, this vector is equal to alpha 1 x1 plus and so on alpha m minus 1 xm minus 1. Okay, then again plus alpha m plus 1 xm plus 1 and so on. This goes up to alpha n xn. Okay, so let's say this is how it is linearly dependent combination, so that this vector xm means, let's say for example somewhere the mth component is there, so like that you have the mth vector. So this m vector is the expressed in the linear combination of other vectors, okay, such that they are not zeros at the same time. So you have the linearly dependence. Now in this matrix, if I want to calculate determinant of A, det A, if I calculate, can anyone tell me what is the value of this det A? So let's say xm is somewhere here, xm is somewhere here, and this xm is equal to this combination. Okay, xm is equal to this combination. Then can anyone tell me what could be the value of this determinant of A? If I calculate determinant of A, then what I'll get? Any idea? Can anyone guess something? Let's say xm is somewhere here, and maybe I have the elements like am, bm and so on, n, m for example. This is the column corresponding to that, and you have these elements, of course. So if I calculate that, if I try to calculate the determinant of this matrix, what value I'm going to get? Fantastic, it's 0, correct? Why it is 0? Because when I'm calculating the determinant of this matrix, okay, I'm interested to calculate this determinant of n by n matrix. When I'm trying to calculate this matrix, determinant of this matrix, if I perform a transformation, xm changes to xm minus this complete combination, alpha 1 x1 and so on plus alpha m minus 1 xm minus 1, because I can perform any transformation I like. Okay, in general, let's say this is c1 c2. If I do this combination, cm changes to c1 m1 plus c2, this is c1 cm, right? So it is cm changes to cm minus alpha 1 c1 alpha 2 c2 alpha m minus 1 cm minus 1 plus alpha m plus 1 cm plus 1 and so on, because I can perform any linear combination whatever I like, it doesn't change. So if I perform this transformation, okay, because clearly I know that my xm, which means nothing but the mth column of that matrix, can be represented as sum of some other columns. Okay, then if I take exactly this transformation, this column will become a 0 column. Yes or no? Correct? This transformation, if I apply this transformation on this column, for example, then this transformation will actually make this complete column as 0, because this is what you have. The xm, this column m, is depending linearly on other columns. So if I do this transformation, it gives me a 0th column, and if all the elements of a column are 0, then this determinant will be 0. Correct? So vector witness column, yeah, of course. Okay, vector has n components, so all those n components are written as a column. So total I have taken n vectors. It's a n by n matrix. Okay, are you all getting this or not? So please do type in the chat box. What we are talking here is, if you know that it is a linearly independent combination, for example, which means mth column of the matrix is equal to linear combination of other columns. Now if I perform a transformation such that this mth column minus this linear combination, because I can perform, it's a determinant, I can do any number of column and row transformations. If I perform this transformation will definitely make this complete elements 0, and in that particular matrix or in that particular determinant we have a column with all 0 elements. Okay, and if you have a column with all 0 elements, ultimately this becomes 0 for linearly dependent vectors. for linearly dependent vectors. Understood? So if they give you any vectors, okay, and if they ask you whether this vector combination is linearly dependent or independent, then ultimately you can check the determinant. Okay, fine. Yes, clear to all of you? So can you please show an example? Yeah, definitely, that's what I'll go up. In fact, I have shown you one here. We'll take the same vectors. Okay, so let's say let x1 is equal to 1 2 3, x2 is equal to 2 4 6, and x3 is equal to, what's the other pair I have taken? Of course, so the other pair I have taken is minus 1 0 2. Okay, fine, minus 1 0 2, of course. So by visual inspection or by lot of experience or something, you know that x2 can be written as minus 2x1 plus 0 into x3. You know this. Okay, so this is what you know. Now let's see, if I take example A matrix as my x1 x2 x3, okay, this gives me the matrix 1 2 3 2 4 6 minus 1 0 2, of course. Okay, so this is my matrix. Now since I know x2 is equal to minus 2c1, x2 is equal to minus 2x1, and I am writing vectors as columns, this ultimately tells me, this equation ultimately tells me that my column 2 is nothing but minus 2 times of column 1, correct? This is what I understand, because I am writing vectors as columns. So this x2 is nothing but my column 2, and this x1 is nothing but my column 1. So from this equation you can understand second column is nothing but minus 2 times of the first column, correct? If C2 is equal to minus 2 times of the first column, let's see what happens. If I want to calculate determinant, det A is equal to ultimately 1 2 minus 1 2 4 0 3 6 2, of course. Okay, now to calculate this determinant you can perform row transformations or column transformations. If you perform this transformation, C2 changes to, since you know C2 is equal to minus 2c1, if I perform this transformation C2 plus 2c1, okay, since C2 is equal to minus 2c1, so minus 2c1 plus 2c1 plus 2c1 cancels each other. If I do this transformation, then ultimately 1 2 3 is what I'll get. Then C2 plus 2c1, C2 is equal to, there is a minus sign somewhere, 2 4 6, okay, this is plus 2, no, sorry, this is plus 2. I think I have done one mistake there, so just come back here, x1 minus x2, yeah, if you shift this minus sign won't be there, no, ultimately, correct. Okay, this is 2x1, because you can see if you shift this x2 to the right hand side, 2x1 plus 0 into x3 is what you have. This minus is not there, sorry, skip it. Okay, so if you do this as minus, then because C2 equal to 2c1, so this combination you see C2 is equal to 2c1, so what I am doing, C2 is equal to C2 minus 2c1 is what I am doing. So if you perform this transformation, these elements are zeros, and we have minus 1 0 2. Now since you have complete this column as 0, this determinant is 0 clearly. Okay, therefore this det A is equal to 0 tells you that one of the rows are definitely linearly dependent on the other, or one of the columns are basically dependent on other. So that means these vectors are depending on each other. That's a linearly dependent combination. Clear? So many times based on this in gate level, they ask you questions like, out of these 9 elements, or maybe 4 by 4 if they give you, then out of these elements they'll miss one element, and they'll ask you if these vectors are linearly dependent, then what would be the value of that unknown. Okay, this is what they ask you. Clear? Did you understand? Okay, now I want to tell you one more thing here. First of all, is this clear to all of you, the concept of linear dependency and independency? Okay, independency we'll discuss anyhow. The concept of linear combinations and the concept of linearly dependence, is this clear? Just a minute here, I'll have water and come back. Okay, understood. Some symbols are going on, thank you. If you see, I'm repeating again, during my teaching, if you have any doubt at any point, please ask. Okay, it doesn't matter how small the doubt is. Clear? Okay, we all are here to learn, and if you already know this, then you need not be here. Okay, so that's why please ask if you have doubts. Okay, like I'm happy that many of you are asking doubts, Hare Krishna, and you know, many others, of course. Guys, actually we are planning for one thing which I want to tell you. In this poll we have the option of conducting a live video call, okay, which of course we'll see during the poll. It's like a one-to-one call, of course, and if you all are okay, then we'll go for a demo, or basically a first session on Sunday at some time, at comfortable time. We'll announce the timing and all maybe in the upcoming 1-2 days, but it's like a video call kind of thing, so that all of you can be on the screen. Anyhow, you will see me, but I'll also see all of you, and we can have some one-to-one talk actually. Okay, shall we do that on Sunday sometime if you are free? Because if it would have been an offline class, I would have seen all of you, but now it's like a bit of online stuff, so sure. Okay, and in that session if you have any doubts or anything, you can always ask me. Of course you're open to doubts at any point during my classes, but still it's like a pure interaction or doubt kind of session, doubt solving kind of session, that's it. Okay, yeah, so let's see. So this determinant is 0. So anyway, now few more things that I want to tell you here is, look, there are 3 vectors, of course there are 3 vectors, but out of these 3 vectors, every vector cannot be written as linear combination of others. Okay, which means if you have a set of n vectors, for example, okay, so let's say you have n vectors. Out of these n vectors, all n vectors cannot be written as combinations of others. Like for example, in this case, if you take x3, okay, if you take x3, this x3 cannot be written as some linear combination of these two. Okay, you can see, because this is 0. If you try to make these two zeros, then this will not be -1. Okay, or if you try to make this as -1, this will not be 0. Similarly, this will not be equal to 2. So like this, we face certain difficulties, which means out of n set of vectors, it's not always possible like you have all n set of vectors being linearly depending on each other, but sometimes you have only some out of these n vectors, only few vectors which are linearly dependent, and then some rest n minus m vectors which are linearly independent actually. Okay, we can have combinations like you can see in this case. Okay, so let's see. First of all, we'll also see linearly independent combinations. Linearly independent combination. Of course, the name itself tells you, you cannot make a vector, you cannot show a vector is depending on other vectors, of course. Okay, that's what linearly independent is. Independent, it won't depend, that's all. Okay, now let's see if a combination, a linear combination, or a set of vectors x1, x1, x2, and so on, xn, are said to be linearly independent. Linearly independent if alpha 1 or summation I equal to 1 to n alpha I xi is equal to 0, only if alpha 1, alpha 2, and so on, alpha n equal to 0. Okay, means you take any vector, you cannot write it as linear combination of others. Obviously it won't depend. Okay, like for example, you see, you write y equal to x plus b whatever, so you can write this because you can know y is actually depending on x. But let's say if y is not depending on x, then you cannot express y as in terms of x, of course. Okay, so that's what even this combination tells you. If you take any vector, let's say for example, if I take xm, let xm is equal to say alpha 1 x1, okay, plus, okay, let's say for example, if we divide this, we have beta 1 x1 plus beta 2 x2 and so on, beta m minus 1 x m minus 1, beta m plus 1 x m plus 1, and so on, plus beta n xn, for example. Okay, so you have this combination, then this combination is said to be linearly independent if, so only trivial solution exists for linearly independent. Yeah, of course. Okay, we'll see. Normally if you have a system, how many linearly independent solutions a linear system of equations can have. Okay, when see if it has a unique solution, of course that solution is linearly independent, clearly we know. Now if the system is homogeneous, it can have trivial solution or non-trivial solutions. We have seen depending on the determinant of A being 0 or non-zero. Similarly, in case of even non-homogeneous systems, if rank of A and rank of A augmented B is equal, but it is less than number of unknowns, then we have seen we have infinitely many solutions. And now out of these infinitely many solutions, it's not necessary that all these infinitely many solutions are basically linearly depending on each other. There could be some finite number of linearly independent solutions. We will know a technique how to calculate the number of linearly independent solutions, of course. Okay, so let's see. First of all, let us understand this word linearly independent clearly. Then we'll slowly progress into the things. Now, this is said to be linear. Let's say if any of these numbers, beta 1, beta 2 till beta n, if any of these numbers is non-zero, for example, then let's say, for example, if this number is non-zero, okay, rest all are zeros. If all these are zeros and if this is non-zero, then clearly this is a dependent combination. Yes or no? This xm is depending on this xm minus 1. If you change this, this will also change. Correct? Now, if this xm has to be linearly independent, then all these betas should be zeros. Only in such case, whatever you do to the vectors, this xm will not change. Correct? Yes or no? 2? Will you all agree with me? Yes or no? Please type in the chat box. I'm telling, if this guy should not depend on, if xm should not depend on any change of x1 to xn, then definitely all betas has to be zeros. Yes? Correct? Yes or no? Everyone? Yes? So, if all betas are zeros, which means all the coefficients are zeros, only then this will not get affected due to change of any of these vectors. That's what linearly independent is. Okay? This fellow will not depend on any of these things. That's what. Okay? Now, ultimately, this beta 1, beta 2, so basically this is the way how you express the linear combination. Now, how to find the number of linearly independent solutions of a system of equations? That's the main concern. So, let's see. And why I am talking about this linearly independent combination also, we'll see. So, clearly here, determinant of x or determinant of A, if A is equal to, if I write x1, x2, all these are again column vectors and so on till xn, it's an n by n matrix. Then the vectors are linearly independent, linearly independent if, in a shorter notation, you can say determinant of A not equal to 0, of course. Okay, just in a shorter way you can tell this, determinant of A not equal to 0, and in the other case we have seen, because of all this explanation, that A is equal to 0 actually. Now, why this story of linearly dependence and independence is actually important for us? That's the main idea. Okay, so let's see. Regarding this concept of eigenvalues and eigenvectors, first of all, I'll give you one point. The number of, this point is actually a bit important again, the number of linearly independent solutions of the system A n by m by n, A m by n, m can be equal to n, doesn't matter, x n by 1 is equal to b n by 1, of course. Okay, so let's say this is Ax is equal to b, for example. B is of course a column vector matrix, it's a vector. So Ax is equal to b is n minus, I'm not proving this result again because it goes beyond the scope of this course, but I'm just showing you. Okay, so this is equal to n, which is number of unknowns, of course, minus rank of A. I'm not proving this result because it takes a, use like 45 to 50 minutes to make you understand this. So, and of course in GATE examination only once this question has come, but still if it comes the other time, you should know that. Okay, that's why I'm giving you this. So out of multi solutions which are, of course if it has a unique solution, then clearly it is linearly independent. Okay, because it has only one solution, there's no other solution to write linear combination. But when you have the cases like linearly or basically infinitely many solutions, then in such case this n minus O of A, number of linearly independent solutions, is what we have for a system Ax is equal to b. Clear? B is m by 1, isn't it? Sorry, yeah, 2. Correct. Sorry, because I was in this sense of square matrix, so I have written so m by 1. Correct. Okay, it should be m by 1 is n minus rank of A. Clear? So please keep this point in mind. Okay, I'm not going this. It's not like I cannot do it or you cannot understand it, but it takes so much time, but which is not relevant to this GATE level of discussion. Okay, that's why. Clear? Now let's see. This linear combination is important because, so one thing you found out, linear, yeah, it's m by 1. Okay, so you can see if the linear if the vectors or if the vectors are linearly independent, then determinant is not equal to 0. Now why we have to study this combination of linear independent and linearly dependent combinations is, whenever we go to the concept of diagonalization, okay, when we go to the concept of this diagonalization, it's really important to know this linearly independent concept. Okay, the reason for that is, let's see, if a matrix has, if a matrix has all linearly independent eigenvectors, say x1, let's say it's an n by n matrix. Okay, so say x1, x2, if a matrix A, let's write here A n by n has all linearly independent eigenvectors, okay, say x1, x2 and so on xn, then we define a matrix P, such that P is of course equal to x1, x2 and so on xn. Of course this is of size n by n again. Okay, so this becomes a size n by n, clearly we have seen. Now if all these are linearly independent, okay, so let's say all these are linearly independent, then we define a matrix P such that P equal to this, and det P not equal to 0, sorry, det P is a matrix of course, so det P not equal to 0, this implies P inverse exist. Okay, so P inverse exist, A is equal to P times D into P inverse. Okay, we can convert any matrix into this form such that it is equal to this P, where P is the matrix which is formed from the eigenvectors, D times P inverse, of course P D P inverse is what you have. And what is this D? D is basically a diagonal matrix. D is basically a diagonal matrix such that D is equal to lambda 1 0 0 and so on 0 0, lambda 2 0 and so on 0, and this goes on 0, this goes on till here lambda n, this zeros comes here, zeros go here. So this is basically a diagonal matrix. D is a diagonal matrix formed by the eigenvalues of this A, and this concept is called diagonalization. If you want to do diagonalization of any matrix, definitely the eigenvectors has to be linearly independent, otherwise you cannot form this P inverse. Okay, because if the matrix which is formed in this pattern is P, and if this matrix is having a 0 determinant, then ultimately this P inverse will not exist, you cannot diagonalize the matrix. Clear? Now why this diagonalization is a very powerful technique, I will show you, just give me some time. But is this clear to all of you? Did you understand? First of all, how to do this? Is this clear to each and every one of you? Yes or no? Type in the chat box, is this clear? Okay, yes, this is, you can maybe put a heading, concept of diagonalization. Concept of diagonalization. Concept of diagonalization. Okay, this is one important concept, concept of diagonalization. And let's see what we encounter here. So why anyone is interested in diagonalization? So if you ask oneself why you are interested in diagonalization, okay, we have plenty many answers actually. Let's say if I give you a matrix, say some random stuff, maybe 1 minus 1 2 3 2 minus 1 4, okay, 7 8 minus 4, something like this. And even though you have a computer, of course, okay, so you have a computer, let's say if I ask you to calculate a power 2024, it's a 3x3 matrix, simple 3x3 matrix, okay. And let's say you got the necessity in your life to calculate what is this a power 2024. Then ultimately it's a laborious process, ultimately, because if you calculate a square, see, first of all you calculate a square, then you'll get a power 4, then you'll get a power 8, then you'll get a power 16, okay. Then a power, a power 16 into a power 16 gives you a power, a power 4 once you get, then you can get a power 16, of course. Then a power 256, a power 512, you go till this, okay, and you keep moving up like this. And ultimately this creates a lot of impact in calculations. But I just want to ask you one thing, why diagonalization? Okay, so why we are actually diagonalizing anything? Why diagonalization? Why diagonalization? This is the most important question one should ask yourself. Then let's see why you want to do diagonalization. First of all, how to do, it's important, but let's see what is the purpose, main purpose to do this, okay. P is how you know how to calculate eigenvectors, you'll calculate, so ultimately you know how to calculate P. So if you know P, you can calculate P inverse. So this D is anyhow, you know the eigenvalue, so you can form D, P inverse. You can check, if you multiply this, you'll get A, okay. Now let's understand one thing here. First point, higher powers of A you can calculate easily. Higher powers of A. Higher powers of A. What is the advantage in calculating higher powers of A? Okay, so let's see. When I give you any matrix, it's really difficult to calculate higher powers of that matrix, of course, because it involves a lot of calculations. But let's say if I give you a diagonal matrix, and if I ask you the higher powers of a diagonal matrix, it's very easy, yes or no? Because if you have A is equal to, let's say if you have lambda 1, 0, 0, lambda 2, then ultimately A power m will be nothing but lambda power m, 0, 0, lambda 2 power m, correct? Because if you do A square, you'll get lambda 1 square, 0, 0, lambda 2 square. If you do A cube, lambda 1 cube, 0, 0, lambda 2 cube. So like that, if you do any higher powers of A, you will end up with this kind of elements, correct? And it's very easy. Whatever the number I give you, it's just raise these eigenvalues, or basically raise the diagonal elements to that number. It's done, simple, correct? Now let's understand something here. If you want to calculate A square, okay, let A is equal to P D P inverse, of course, okay. So P D P inverse. Then if I calculate A square, this implies A square is equal to P D P inverse times P D P inverse, of course, okay. So you have P D P inverse. Now you know matrix multiplication is associative. You can write this as P D P inverse P times D P inverse. So this is P D. This is identity matrix. P inverse into P is identity, of course. So this identity into D will again give you D times P inverse, and D into D gives P D square P inverse. And if you do this job and so on, you can get A power m is equal to P D power m P inverse. That's it, okay. So now whatever the matrix I give you, once you know the eigenvalues of that matrix, then it's dead easy for you to calculate any higher power of A. Clear? Yes or no? Please type in the chat box. 2. Will you agree? Yes or no? Please type in the chat box here. Are you all understanding or not? It's almost 20 minutes, only 40 minutes left. Please type in the chat box quick, a bit fast. Alex, Deepankar, Sagnika, all of you. Yeah, Gautami. Okay, now so this we can calculate higher powers of m very easily. The second case I would tell you is calculating solutions of linear equations is also a bit very easy. Solving linear systems is also very easy. Solving linear systems, like especially in the cases where delta A is equal to 0, okay, especially where, let's say if the system is Ax equal to B, then where det A is equal to 0, of course, okay, where det A is equal to 0. In such cases also we can we'll see we can apply this technique, okay. Even if you have 0 as an eigenvalue, still the matrix can be diagonalizable, okay, because 0 as an eigenvalue will only affect the rank but not the diagonalizability of the system. Clear? So anyway, let's see. If you observe, you have the system Ax is equal to B, for example. Okay, Ax is equal to B. Now let's say you got the matrix has you try to diagonalize it and it got diagonalized successfully. Okay, then you can understand one thing. This A can be written as PD P inverse into X is equal to B, of course. Correct? Now let's see. This is equal to D into P inverse X can be written as, if this P, if you multiply with P inverse on both sides, this is P inverse into B. This is what you will get. 2. Yes or no? Please type in the chat box. Is this clear to all of you? You have PD P inverse acting on X is equal to B, of course. And if you multiply with P inverse, because if P exists and P inverse exists, it's a diagonalizable combination, so P inverse exists by default. So if you multiply with P inverse on both sides, this P inverse into P gives identity matrix. I into D is again D. P inverse into B, this P inverse into B comes here. Now let's see. Let P inverse X is equal to Y, for example, and let P inverse B. This is one matrix multiplication into a column vector, maybe some other B cap, let's say. Okay, so B cap, maybe some other matrix you'll get, because this is just multiplication of a matrix with a column vector, so that gives some different vector. So let's say maybe I'll write B tilde. Okay, so let's say this is what you get. One advantage here is, look, when you do this transformation, it's not transformation, basically if you do this multiplication, it is a diagonal matrix. Okay, this is a diagonal matrix and this vector is actually Y. Now you can see, if you just expand this slightly and observe what happened. Lambda, let's say 3 by 3, I'm taking 3 by 3 to make the job easy. Lambda to 0, 0, 0, lambda 3 and so on. You have n lambda n if you have n by n matrix. This gives you Y1, Y2, Y3, because this is again a vector, is equal to maybe say B1 tilde, B2 tilde and B3 tilde. Maybe these are some constants, of course. Okay, so that's what. Now in this system, you can easily calculate what is this vector Y. Yes or no? Correct? This Y can be easily calculated because if you just multiply lambda 1 Y1 is equal to this element. So Y1 equal to B1 by lambda 1, Y2 equal to B2 by lambda 2, Y3 equal to B3 by lambda 3. So this is what you get. So if a matrix is diagonalizable, then it is semi-positive definite. We'll see. Okay, what is semi? I think in the last class I mentioned, but that has nothing to do with this. Okay, we'll see. Clear? Semi-definite or semi-positive semi-definite or negative semi-definite, that depends on the eigenvalue being 0 or not. We'll come there. Okay, but let's see here. So whenever you have this system B1, B2, B3, of course, then you can see lambda I Yi is just equal to Bi tilde. Correct? Yes or no? Lambda 1 Y1 is equal to B1, lambda 2 Y2 is equal to B2 cap, lambda 3 Y3 is equal to B3 cap, and so on. That's what you have. So for getting any value of Y, this is what the equation you have. Yes? Correct? That means your Y is easily calculated. That implies Y is known. You can calculate this because you know these elements, you know these elements. So ultimately you can calculate what is Y. If Y is known, what is Y? P inverse X. So if you want X, just multiply P to Y, you will get the answer. That's it. Okay. So since P inverse X is equal to Y, this guy tells you X is nothing but P times Y. P is known, Y is known. That means you can calculate X. That's it. Clear to all of you? Yes or no? Please type in the chat box. Is this clear to each and every one of you? Okay. Did you understand how diagonalization helps you in solving systems just with the help of multiplications? Okay. You need not calculate inverse, cofactors, nothing. Okay. Just this simple technique, whatever I have done. Only one inverse you have to calculate is for P. Okay. That's it. Once you calculate that, then there is nothing complexity in this. Okay, clear? So but for this to happen, this P should contain all the eigenvectors to be linearly independent. That's it. Okay, like for example, you see, if you take this example of diagonalization, example of diagonalization. Okay, anyway, if you take example A is equal to 4 2 2 2 4 2 2 2 4, it's a symmetric matrix, of course. Okay, I have taken a symmetric matrix so that the job is a bit easy. Then so in matrix, the time toughest chapter in maths. So is matrix the time toughest chapter in maths? What is the meaning of time toughest? I didn't get you. Okay, anyway, you define what is time toughest, then I'll be able to answer. Now anyway, let's see whether you can diagonalize this, whether, because I want to show few properties again. So whether can we diagonalize this? Diagonalize. Okay, so let's say I give you matrix. How do you decide whether we can diagonalize this or not? So first of all, you calculate the eigenvalues. Lambda, if you calculate, we have calculated 8 2 2, and eigenvectors, if you calculate x1, we have calculated 1 1 1, x2 we have calculated, it is -1 0 1, and x3 is something like -1, I think 1 and 0, correct? Yeah, this is what we got. Maybe these two can be flipped, doesn't matter. That's a time accidental game. Is the matrix the toughest chapter in maths? No, yeah, why not? Actually, see, I'm telling you, there are two ways to look at things. One is the things being toughest, the other is the things being more useful. The toughest things are obviously the most useful things. Okay, definitely in life also it holds. You know, GATE is tough, but definitely why you're writing GATE? Because you guys want to take the uses of GATE examination, correct? Or benefits of GATE examination. That's what. If something is toughest, definitely it's the most useful thing in life. Okay, calculus is toughest. Oh my god. Fine, we'll see when it comes to the story of calculus. See, basically it's nothing like toughest or easy or you know, things, but see, it's one thing is you should always have the you know, enthusiasm to learn things. Okay, and of course I think I'm not boring you too much. I'm explaining you graphically whenever possible, okay, and teaching you some in a understandable way. Okay, I think I'm not boring you too much. Then coming to the main things like which is toughest or which is easiest, there's nothing like toughest or easiest. Okay, few things can be easily understood, few complicated things can also be easily understood if you have a nice teacher. Again, star mark, terms and conditions apply. Okay, if you ask me my favorite chapter in maths, okay, so it is like numerical methods. Okay, the reason is numerical methods provides you solution to a lot of equations which basically analytical methods cannot solve. Okay, like for example, if I give you a fourth order equation, okay, let's say if I give you ax power 4 plus bx cube plus cx square plus dx plus e equal to 0, if I give you this equation, ultimately you don't have a standard technique to solve that equation. Okay, but numerical methods solve it. Okay, if I give you x power 0.8 minus 2 x power 1.9 is equal to things like that, analytical methods cannot solve, but numerical methods can solve. Okay, in fact, I'll give you one integral. Will you all solve? Will you all tie it? I'll give you one integral actually. Will you all tie that? Yes. So have you worked as a researcher? Yeah, in the past, of course. Okay. You all know, if I ask you the answer of integral root of integral 0 to pi, let's say, root of 1 minus x sine square d sine square x, or pi by 2, let's say, to make the job easy, sine square x dx. If I ask you this integral, you know, many of you will be very happy. You will see, okay, you'll understand. So ultimately you let, since sine square x is less than 1, so you let this is cos x is positive within the 0 to pi by 2, so integral cos x dx minus sin x dx, put the limit 0 to pi by 2, you'll get some answer. Okay, -1 is the answer, done. Of course, okay, 0 to pi by 2 cos x dx, so integral of cos is minus sin. Okay, so minus sin pi by 2, -1 minus 0, of course. Can anyone tell me what is the value of this? Just here it is 1, so I have changed the constant 1 to 0.2, that's it. 0.2 or anything in general. Okay, 0.1 you can keep any number whatever you like, but make sure this is always real. Okay, so that's why I have intentionally taken that number to be less than 1. So take this number to be less than 1 so that you don't enter the complex field, live in the real field, so that life is simple. So if you calculate this, I'm telling you, you try this and tell me in tomorrow's class. Okay, you calculate this integral and you calculate this in, and you calculate till tomorrow and tell me in the next class. I'll be see how many of you will be able to solve this. Okay, chalo, you can try tools also if you want. Chalo, let's see. Well, what we're teaching. So whether this matrix is diagonalizable. Good. So how to observe whether this matrix is diagonalizable or not? So first of all, you form this matrix P. P is equal to x1, x2, x3. So 1, 1, 1, minus 1, 0, 1, minus 1, 1, 0. Okay. So this is what we have. So if you calculate determinant of P, that P is equal to 1 into minus 1 plus 1 into 0 minus 1 minus 1 into minus 1 into 1, of course. Okay, so this is minus 3, which is not equal to 0, of course. 2, because 1 into 0 minus 1, you have 1 of minus 1, minus of minus is plus 1 into plus 1 into 0 minus 1. So this is minus 1 again, this minus 1 into 1. So total minus 3. This is non-zero clearly, so you can calculate P inverse. Okay, so since that P not equal to 0, P inverse exists. So A is diagonalizable. We know this. So A is diagonalizable. You can actually diagonalize A. Done. Okay. Now let's see some important things. I would like to define two terms which are called algebraic multiplicity and geometric multiplicity. Okay. We'll see algebraic multiplicity of a eigenvalue and geometric multiplicity of an eigenvalue, which is actually a bit important as well. So first let us come to algebraic multiplicity. Algebraic multiplicity of an eigenvalue. Of an eigenvalue. Okay, so algebraic multiplicity of an eigenvalue. Okay, so ultimately what you will get is you know, a real number or basically a okay fine, a real number, integer, in fact a real integer, of course integer is a real integer. What letter we shall use? Maybe which number we shall use? Okay, x is said to be algebraic multiplicity of m. Algebraic multiplicity of an eigenvalue, multiplicity of an eigenvalue lambda if lambda appears x times as eigenvalue of A, as eigenvalue of A, of course, which means, for example, if you calculate eigenvalues, okay, then if you calculate eigenvalues, let's say a particular eigenvalue is coming 4 times, then we say the algebraic multiplicity of that eigenvalue is 4, okay, because it's coming 4 times. Algebraic is just counting. Clear? Now let's say, for example, I'll again pick this matrix, which is my favorite. It is also many things, 2 to 4. If you calculate lambda, you'll have 8 to 2, correct? We have seen lambda equal to 8 to 2, of course. Then we'll see algebraic multiplicity of lambda equal to 8 is 1. Algebraic multiplicity of lambda equal to 2 is 2, of course, okay, because it's 2 is getting repeated once. So total the 2 times 2 is getting visible in this eigenset. So this is 2, of course. Now what is geometric multiplicity? Let's see. Geometric multiplicity. Geometric multiplicity, you can see geometric multiplicity is nothing but geometric multiplicity of an eigenvalue lambda is, okay, is rank of A minus lambda I. Rank of A minus lambda I. Okay, again these are all very powerful theorems which I'm not proving as of now, so I'm just giving the results. So rank of A minus lambda I, of course. Okay, now This has very important significance with the diagonalization concept. Okay, why? What is the connection between this algebraic multiplicity and geometric multiplicity? We'll see now. And most importantly, you'll see algebraic multiplicity is always greater than or equal to geometric multiplicity. This is one very standard condition. And whenever things are diagonalizable, okay, if this matrix capital A is diagonalizable, for any eigenvalue, these two will be same. Clear? I'm repeating. If a matrix is diagonalizable, then any eigenvalue will have same algebraic and geometric multiplicities. Clear? Please make this point. I'm writing here. If a matrix is diagonalizable, if a matrix A n by n is diagonalizable, then arithmetic multiplicity is equal to geometric multiplicity of any eigenvalue. Then for an eigenvalue lambda, we can write for an eigenvalue lambda of A n by n of A n by n. For an eigenvalue lambda of A n by n, we have algebraic multiplicity is equal to geometric multiplicity of this eigenvalue. Clear? So where can I find notes? In this video, you have the description in the PW app. So where if you click on the link, it directs you to the note, the lectures. Okay, and in the lectures tab, beside you have the notes tab, so you can click the notes. Clear? So now let us see how to identify things. Okay, so how to calculate the rank of A minus lambda? You know how to find the rank of any matrix, of course. So let us take this matrix A. We found one thing for this matrix. Okay, so for this matrix, sorry, of course this is also the same matrix. For this matrix, we found P, and P is not equal to 0, so P inverse exists. So which means this matrix can be diagonalized. Okay, so which means if you want to diagonalize this, A is equal to P D P inverse. You can calculate the inverse of this. Right now, since we are using smartboard, I'll take the advantage of this inverse calculator, inverse of matrix calculator. You can use, there are plenty of calculators nowadays. You have a lot of linear solvers. So my matrix is of size 3 by 3. So set matrix. So what is the matrix actually I have? 1 minus 1 minus 1. You can use these tools many times. Okay, I keep using these all my life. 1 minus 1 minus 1. Then after, this is 1, this is also 1. You put 0 at one place and 1 at other place. Then this is 1 and this is 0. Correct? This is the matrix I have. Minus 1 0 1. So minus 1 0 1 minus 1 1 0. Correct? Okay, so minus 1 1 0. Correct? This is the matrix. Okay, so calculate. I'm giving this instruction, calculate of matrix inverse. So this is my inverse. Okay, so if I take 3 outside, for example, P inverse is going to be 1/3 if you take out, because 3 is there in every element. So if you take 3 out, 1 1 1 minus 1 1 2 1 1 1 minus 1 1 2, of course. Okay, so minus 1 2 actually, this is also minus 1. And then after, what is the last? Minus 1 2 minus 1 minus 1 2 minus 1, because you know how to calculate inverse. Even in your casuals you can do it. So please a question like समझ दीजिए. That's what I'm doing. Okay, what is algebraic multiplicity? It's basically the number of times eigenvalue comes in when you calculate the eigenvalues. That's it. Okay, like I have given you an example here. When you calculate this, you'll see 8 is coming only once. Okay, so algebraic multiplicity of lambda equal to 8 is 1. Okay, because you can see 8 only once in this case. But algebraic multiplicity of lambda equal to 2 is 2, because 2 is coming 2 times in this complete eigenvalues. That's why its algebraic multiplicity is 2 actually. Clear? Now let's see, you got this P inverse. Okay, so now when you multiply this P D P inverse, you know that's P inverse. So P inverse exists for this matrix. Okay, which means this matrix is diagonalizable. You can write A as this 1 minus 1 minus 1 1 0 1 1 1 0. Then after 8 0 0 0 2 0 0 0 2. Then after this 3, I'm pulling it here. Maybe it's a constant, so we can pull it up. 1 1 1 minus 1 minus 1 2 minus 1 2 minus 1. This is diagonalized splitting of this matrix, which means if you multiply these 3 things with this 1 by 3, you will again get A. You can check if you want. You'll definitely get it. Okay, so anyway, coming back to the story, If this is the case, if matrix is diagonalizable, then ultimately algebraic multiplicity and geometric multiplicity will be same. Let us check whether this statement is correct or wrong. Okay, we take this matrix 4 2 2 2 4 2 2 2 4, okay, which is a bit easy to analyze. Now lambda is equal to 8. You have seen lambda is equal to 8, of course. Okay, so when you take lambda equal to 8, algebraic multiplicity of lambda equal to 8 is equal to 1, okay, because you know ultimately it has 1, of course. If you take lambda equal to 8 is coming only once in the complete eigenspectrum, so it's 1, of course. Sorry, so can you tell me how product of eigenvalues is equal to sum of principal minors? I'm not telling product of eigenvalues is principal minor, product of eigenvalues is the determinant, okay, but taking two eigenvalues at a time and making the summation, that gives you sum of minors. Okay, in the last lecture, by looking at the matrix, how we can actually check the this characteristic equation. Okay, just by looking at the matrix, how we can write the characteristic equation, I have taught you. So please just visit one video before this, you'll get the idea. Clear? Now let us calculate the geometric multiplicity. Geometric multiplicity of lambda equal to 8, for example. Okay, now if you calculate lambda equal to 8, since this matrix is diagonalizable, you will find out this geometric multiplicity of lambda equal to 8 is also 1. Okay, how we can do that? First consider the matrix. Consider a minus lambda I, so a minus 8 times I. So if you see, let's say b is equal to a minus 8 times of I, so 4 minus 8, which is minus 4, 2 2 2 minus 4 2 2 2 minus 4. Okay, this is what we have. Then if you perform these transformations, let's see, R2 changes to, okay, R2 changes to 2R2 plus R1. Similarly, R3 changes to 2R3 plus R1. If you perform these two transformations, because to know the rank, I'm just trying to convert in echelon form, that's it. So if you convert this to echelon form, B is equal to this is first order remains as it is, minus 4 2 2, of course. Then coming here, 2 2's are 4, 4 plus minus 4 0. Then 2 into minus 4 minus 8 plus 2 minus 6. Then after 2 plus 2 2's are 4, 4 plus 2 6. This is what we get. Coming here again, we have this is 0, this element is 0, of course. Then after this 2 times of 2 plus 2, we have 6 here. And then after this minus 4 is 2 into minus 4 is minus 8, minus 8 plus 2 is minus 6. Okay, so you have minus 6. Then ultimately this is not in echelon form, so if you make this to echelon form, you'll see R3 changes to R3 plus R2. So if you make this, we have minus 4 2 2 0 minus 6 6. Okay, and this becomes 0 0 0, of course. So this rank is coming up to be 2, right? Rank of a minus lambda I, 8i. If you take 8i, so minus 4, this turns out to be minus 4. This is correct? Yes. A minus b, I didn't understand this part. See, since I'm interested in doing a minus lambda I, okay, I'm doing a minus lambda I, of course. Then a minus lambda I, okay, so this is a minus 8i, so this is a minus 8i. So if you do this a minus 8i, then ultimately 4 minus 8 times of I gives you minus 4. Similarly, these are minus 4s, these 2's will remain in the spots. So if you want to make these two zeros, for example, 2R2 plus R1, 2R3 plus R1, so minus 4 2 2, 2 will give you what it will give me. It gives me 2R2 4 plus minus 4 0, this is also 0. Then minus 8 plus 2 6, minus 8 plus 2 minus 6, then 4 plus 2 6, of course, then 4 plus 2 6, and this is minus 6 2. So if you convert it to echelon form, because this is not in echelon form, then 0 0 0 is what you're getting. Okay, so this is giving you rank is equal to 2, correct? So just a minute, then we'll modify this statement. I guess we have am is equal to gm, or sum of am is equal to sum of gms. Just a minute, we'll confirm this point, because since I'm not deriving these points, it happens sometime I can commit things. So rank of a minus 8i is equal to 2, of course. Okay, so you can see this is what you get. This is the geometric mean, of course, in this case 1 So rank of A minus lambda I, if you do lambda I is this, so this is coming up to be 2. Fine. Let's say if you go for lambda equal to 2 case, then we'll decide what to do. For lambda equal to 2, okay, so A minus 2i, if you calculate this A minus 2i, this matrix becomes 2 2 2 2 2 2 and 2 2 2, of course. Okay, so ultimately this gives up things like if you apply R2 changes to R2 plus R3, sorry, R2 minus R1, R2 minus R1, and R3 changes to R3 minus R1, then ultimately this A minus 2i is equal to A minus 2i is equal to 2 2 2. This is equivalent to, then these are zeros ultimately. So this tells you rank of A minus 2i is equal to 1, correct? Yeah, 2. So this is sum of algebraic multiplicities. Yes, 2. Sum of AMs should be equal to sum of geometric multiplicities of the eigenvalues. Yeah, that's what it has. Okay, so this is what you have. Sum of algebraic multiplicities will be equal to sum of geometric multiplicities. This is 2. Okay, so basically if the matrix is non-diagonalizable, what happens? This sum of arithmetic, sum of algebraic multiplicities, which is nothing but the total number of eigenvalues, will be greater than this. Okay, if you take any matrix which is non-diagonalizable, then ultimately this sum of algebraic multiplicities would be definitely greater. Okay, this geometric multiplicity sum will not equal the arithmetic multiplicities. Okay, so that's what we can see in this case. Yeah, this is 2, this is 1, of course. So this 1 plus this 2 gives 3, correct? Yeah, of course. Okay, so this diagonalization, basically if you keep talking again, it's a very vast subject, but of course we are restricting ourselves to the point within the gate examination. Also, I would like to give you one more point actually. You'll see that for a matrix n by n, A n by n, rank of A can be written as n minus algebraic multiplicity of 0 as an eigenvalue. Algebraic multiplicity of 0 as an eigenvalue, of course. Okay, so for matrix, how many eigenvectors can we have? Can we get actually? Eigendirections is what we'll get actually. So that can be 3 or 2 depending upon the what is it, the type of matrix what we get. Because it's like if you have 2 directions, but these 2 directions can be linearly. If you have 3 directions like this, then the third direction, if it's like in the plane, then it's like a linear combination. Okay, like if you take any 2 vectors, any vector in that plane can be written as linear combination of these 2 vectors. Okay, that's how it depends on the type of matrix, of course. Okay, and I would like to give one more interesting point here. Number of linearly independent eigenvectors of a matrix independent eigenvectors of a matrix is equal to the number of linearly independent eigenvectors of a matrix is equal to number of distinct eigenvalues of that matrix. Number of distinct eigenvalues of the matrix actually, of the matrix. Clear? This point is also very important point. Clear? It's a shortcut method to solve rank. Yeah, of course. Okay, bringing any matrix in a echelon form will drastically reduce the steps. Okay, so all these are important things. And like for example, you see for a matrix A n by n, rank of A is equal to n minus of algebraic multiplicity of 0 as an eigenvalue. Like for example, you take this matrix, basically this matrix 4 2 2 and all. This matrix has eigenvalues lambda equal to 8 2 2, of course. Okay, so in this eigenvalues there is no 0, so definitely if you calculate determinant, this is a non-singular matrix, which is also evident if you do the product of these elements, then ultimately it's non-zero. So this matrix has a rank 3, and that 3 is because 3 minus there is no 0 in this case, so that's why this term algebraic multiplicity of 0 is 0, so 3 minus 0 is 3. That's how the matrix rank is 3. So all these points are connected. You may feel why I can learn all these points, because if the matrix is still 3 by 3, it's nothing, it doesn't make much sense because you have your traditional methods. But if matrix goes beyond, okay, beyond your control, like let's say for example if you have 40 by 40, 90 by 90, 100 by 100, then these kind of techniques definitely help you a lot, and which exclusively we use many times in data science algorithms. Clear? So for one eigenvector there will be only one eigenvalue, right? Yeah, 2. For one eigenvector there is only one eigenvalue, and it can be possible for 2 eigenvectors there is same eigenvalue, like we have seen in this case. Okay, is this clear to all of you? Are these points clear to all of you? I hope many of you might have learned many new points today in the aspects of diagonalization, okay, and then after this linearly dependent independency, because all these are important in especially ECEEE, then computer science and data science exclusively. This diagonalization concepts are basically this linear dependence, independence are very much frequent. Okay, that's why frequent in the sense not in gate paper, but whenever we try to write some machine learning algorithms or basically DS algorithms, data science algorithms, this especially will deal with some systems called sparse systems. Okay, so in case of sparse systems, when we go for diagonalization, basically a sparse system is where many of the elements in a matrix are 0. Let's say for example if a matrix is of size 100 by 100, okay, then you have 10,000 elements in that, but out of that 10,000 elements, let's say only some 1200 or 1300 elements are non-zeros, remaining all are zeros. Then your computer space, your computer takes a lot of space to save this 10,000 elements. Okay, so then we'll write efficient algorithms by doing sparse systems and all. Clear? So that's why we generally use this concepts of diagonalization, all these things. Have you ever heard this word sparse systems? S-P-A-R-S-E, sparse. Sparse systems, S-P-A-R-S-E, sparse systems. No. Okay, anyhow, in the tomorrow's class I'll teach about the block systems. Okay, then we'll see some sparse systems like tridiagonal systems. Okay, or maybe we'll see block matrices. We'll deal these kind of things. Okay, so we'll deal all these things in tomorrow's lecture, of course. It's not sparse actually, sparse. Okay, S-P-A-R-S-E. So if I find different eigenvalues for matrix only, right? Yeah, so there is no relation between eigenvectors. See, for a matrix decides a direction. See, for example, if you calculate lambda, okay, then lambda and x are depending on each other. Okay, so lambda and x is called eigenpair. Okay, so for every xi you have a fixed lambda, for every lambda you have a xi, of course. Okay, and see, whenever lambda and xi form a pair, then these two, it is as a pair. This pair depends on the given matrix. Understood? It's not like every matrix will actually have eigenvectors along a fixed direction, right? Depending on the matrix, you have different directions. Clear? That's what. Now, let us solve one question. Maybe we have spoke a lot about this eigenvectors. Now you tell me this number of linearly independent eigenvectors of this matrix. So integer type. I'm giving you 45 seconds. Maybe start. Come on, do it. Number of linearly independent eigenvectors of this matrix. So how do you find linearly independent eigenvectors? I have just given you one hint. Okay, so let's see. First of all, one thing that I told you is number of linearly independent eigenvectors is equal to number of distinct eigenvalues. Correct? This is what we have told. Number of distinct eigenvalues. Okay, so number of distinct eigenvalues. Now clearly, if you see what are the eigenvalues here, for given a, eigenvalues are nothing but, do you understand one thing? This matrix is actually upper triangular matrix, because if you take the lower diagonal, all these elements are zeros. Okay, lower triangular, then all the lower triangular elements are zeros. So ultimately this is a upper triangular matrix. So for any triangular or diagonal matrix, the eigenvalues are nothing but the principal diagonal elements, correct? So lambdas are 2, 2, 3. Now here you can see one eigenvalue is repeating, therefore number of distinct eigenvalues is equal to 2, because you have 2 and 3, only 2 distinct different eigenvalues. So distinct eigenvalues is equal to 2, of course. Okay, so number of distinct eigenvalues is equal to 2. So this implies number of linearly independent eigenvectors is also 2 in this case. Okay, so 2 is the correct answer actually. Clear? Okay, I understand. Maybe people are interested in calculating the eigenvalues, but this is a upper triangular matrix, so ultimately the diagonal elements themselves are the eigenvalues. Okay, so let's go to one more question maybe. So solve this question again. I'm giving poll, single choice, maybe 60 seconds. Okay, 60 seconds, fine, good. The matrix M has eigenvalues -3, -3, 5. An eigenvector corresponding to eigenvalue 5 is -1, 2, -1 transpose. One of the eigenvectors of M cube is dash. Options. Faster, a bit, quick. The concept of diagonalization is also like a decomposition of a matrix, okay, into a matrix, diagonal matrix, P inverse, which is something similar to SVD, singular value decomposition, which we'll see tomorrow, of course, in a detailed sense. And if you guys are interested in learning much about linear algebra, I suggest you a book, which just a minute. Fine, so let's see. I've told you one important point. Eigenvectors of A and A power M are same, correct? We have in fact shown this. So if this is eigenvector, so let's say x is equal to 1, 2, -1 for example, then ultimately if this is eigenvector of A or M, whatever, this is also eigenvector of M cube. Okay, so 1, 2, -1, this will also be eigenvector. Clear? So B, which is 1, 2, -1, if this is eigenvector of A, then ultimately this is eigenvector of M cube, M power 5, whatever, so it acts as an eigenvalue. Intentionally I have given this option 8. This is actually a previous year question, of course. They have given this 8 here because whenever there is a cube, many people think that if you cube these elements, you'll get this vector. Okay, but eigenvector is not eigenvector cube. Okay, it is only the same eigenvector, which we have written the point today when we are talking about eigenvectors. Clear? So we can see 1, 2, -1, of course. So this is what we get. One of the eigenvectors of M cube is also this 1, 2, -1. So B is the correct answer. Let's see. Ashwini Kumar Biswal, right? Okay, yeah, correct. B is the correct answer. So let's go to the next question. So this is slightly fine. Okay, I've told you one important point actually. Rank of A is equal to rank of A plus 2i, then rank of A minus A. Okay, I'll give you this question as homework. You can try. In fact, you want to learn one point if you want to solve this question. Okay, homework question. So what is the point? Let's say if you have an equation with roots, let's say for example, I'll give you a hint here, with which you can solve this thing, of course. So let's see. The hint is, if you have an equation, if x square minus 5x plus 6 is equal to 0, you have two-degree equation, then roots are alpha 1 equal to 2 and alpha 2 equal to 3. These are the roots. Correct? Now if you want an equation whose roots are alpha 1 plus 1 and alpha 2 plus 1, let's say, okay, so for example you have roots like alpha plus beta, alpha and beta, okay, so let's say, because these are the familiar words, alpha and beta, then let's see, if you want a polynomial or equation whose roots are alpha plus k and alpha minus k, alpha plus k and beta plus k, of course. Okay, so equation with roots alpha plus k comma beta plus k. If you want to check this, then the equation would be something like, then equation with roots is, if this is f of x is equal to 0, for example, then this equation is f of x minus k is equal to 0. Okay, f of x minus k is equal to 0 is the equation which will have the roots alpha plus k and beta plus k. Like for example, you check here in this equation, you know, alpha equal to 2 and beta equal to 3. If I want an equation with alpha plus 1 and beta plus 1, okay, example, for equation with roots, okay, so with roots, this is 2 and that's 3, of course. So let's say alpha equal to 1 or maybe 3 and beta equal to 4. Let's say I have increased the roots by 1. Then this implies, you know, x square minus 7x plus 12 is equal to 0. This is the equation. But you can get this equation from this equation because you are actually increasing roots by 1. So what you'll do is f of x minus 1, which is consider this is f of x. So you consider x minus 1 whole square minus 5 into x minus 1 plus 6 is equal to 0. Okay, because I have increased my roots by 1, so function will actually decrease by 1 in x. So if you simplify this, x square minus 2x plus 1 minus 5x plus 5 plus 6 is equal to 0. So x square minus 2 minus 5 minus 7 plus 1 plus 5 6, 6 plus 6 12. Okay, so whenever you increase the roots by k, then the function of x minus k is equal to 0 will be the exact equation fitting that roots. Clear? So if you know this point, this is just a hint to solve this question. So this is actually one of the previous year question in XC where maths is very tough actually, and in that exam only I have only in 4, of course. So I'm just giving this question as homework question. Clear? So this is actually the homework question for you today. Okay, clear? So I think I have put few more questions, but it's okay, we'll go tomorrow. So anyway, we'll see LG decompositions and SVDs, which is similar to diagonalization, in tomorrow's lecture in detail, and then we'll see this block matrices, okay, partition matrices. With that we'll close the syllabus. Okay, vector spaces also, of course, today. Vector space again a very basic concept. Vector space and subspace, we'll calculate row spaces, column spaces and all. We'll see how to do that, and tomorrow will be the last lecture of linear algebra. Clear? So can you please tell how to write short notes, please? I'll tell this on maybe tomorrow, okay, because one chapter gets finished, so you can you'll get the idea out how to write that. Okay, and in on our channels we have made a lot of videos how to make short notes, why short notes is important, all these things. So definitely please you can have a look at that. So basically in today's class, what all we have taught, I have forgotten. We have told many things today. So we started with the concept of eigenvectors, then we went into linear combinations, and then we went into the concept of diagonalization, then after few properties. Okay, good. So let's see what all we have discussed today. So we started with eigenvectors, of course, then we looked at linear combinations, linear combination of vectors. I hope you all have understood it clearly now. There is nothing complexity in this. Linear dependency and linearly independent. Then we have given formulas for linearly independent solutions, number of linearly independent eigenvectors. We have given the solutions of this. So we'll teach applications. Applied maths is not involved in this part, of course, because right now this channel is dedicated exclusively for GATE. Okay, so that's why I'm not teaching as of now. But maybe in future, after, you know, when I'm teaching technical subjects, definitely we'll find a lot of applications. And then, but of course, I'll teach for mechanical in general. So, yeah, but I'll give you good differences. You know, if for learning many good points in linear algebra, if you want to get very good insights by Gilbert's triangle. Gilbert Strang. He's a professor retired at Massachusetts Institute of Technology, MIT, basically, and for almost 50 years he has taught the course there, linear algebra. He has many books, machine learning with linear algebra, or linear algebra with probability. We have a lot of things. Okay, so this linear algebra by Gilbert Strang, he's a retired professor at again MIT. So this is one book, and also this book itself is self-sufficient. It dives you to many good points. Okay, in fact there are lectures of him on YouTube as well. So but they were very old, 2008 or 9 when he was teaching one of the courses at MIT. They were available. You can just log in and you can just check it out. Okay, but of course not the complete thing is needed for GATE examination. So I have picked only few points from his lectures. Okay, I borrowed few points from his book and many other plenty resources of linear algebra, so to teach this course. Okay, right from day one. And we have also talked about a bit of diagonalization. We have seen some good insights again of diagonalization. So all these are the points that we have discussed today. So briefly, tomorrow's lecture will be rounded about, is it also for mechanical? Every class what I'm teaching is also for mechanical, right? See, I'm telling you again, all this stuff I'm covering to all the branches what I have given. But for if you are here and if you want to look for your own syllabus branch, please look at the official syllabus, and because every branch has got certain variations in engineering maths, so please go through your syllabus detailedly and please focus only on those topics. Clear? So book recommendation for mathematics for GATE. In the first lecture I have given Vishwadeep, basically it's B.S. Ghewell is a good book to start with. Okay, B.S. Ghewell, the fat book which you find, is a nice book to look at many things, but exclusively for linear algebra. If you future looking in data science or in other computer aligned subjects, then this book is a very good book to start with. Okay, and in fact he has written many books. Of course there are 2 or 3 nice books of him. Machine learning with data science, machine learning with linear algebra. Okay, we have a lot of algorithms, but again this is a very good book. Fine. Okay, so anyway, if you are okay, then so this question, please solve it as a homework. It's a homework question for you. I've just given a hint to solve this. Then again we'll meet tomorrow at 7 p.m. So tomorrow will be the last class of linear algebra, which is again some nice concepts we'll see, basically solving of system of equations, and along with that vector spaces, then SVD and partition matrices also we'll see. Okay, so a bit, and then we'll, of course this batch is in English, and we'll meet 7 p.m. daily. So tomorrow is the last lecture for linear algebra, so do attend without fail. In the last I'll revise all the complete linear algebra whatever we have done, and that's it. Okay, so we'll meet tomorrow at 7 p.m. sharp. Any doubts or any questions you can ask me. So if you all are okay with the 1-to-1 session, we'll plan something on a Sunday. Okay, I've given you homework regarding practice problems. I'm planning to upload one sheet on this Telegram channel of mine very soon. Okay, maybe by this Sunday, or by this Sunday hopefully I'll upload one on linear algebra and one on single variable calculus. Maybe for the 3-4 lectures what we cover, I'm planning to upload one. So if it is diagonalizable, one eigenvalue is 0, then other eigenvalue pairs are the same, like 0, 3, 3 as it, or is it like 0, 3, 5? So I didn't get this question, just a minute. If it is diagonalizable, then one eigenvalue is 0. Okay, the other eigenvalue pairs are the same. What do we mean by other? It can be distinct or it can be matching. Okay, see, it's not like if one eigenvalue is 0, then you cannot diagonalize this or not. Okay, we can actually diagonalize. The only condition is these eigenvectors has to be linearly independent. That's the main condition. Okay, so the main check for diagonalizability is the linearly independentness of the eigenvectors. Clear? And whether the eigenvalues get repeated or they don't repeat, that depends upon the matrix again. Okay, say if one of the eigenvalues is 0, it doesn't mean that all other eigenvalues should be distinct. Okay, they can repeat. It can happen. Okay, so any more things to do or to discuss with? Okay, so tomorrow it will be the last lecture of linear algebra. We'll look at a bit of vector space and SVD and projection matrices. So can you please tell how to handle multiple subjects at the same time, or should I learn one at a time? You can handle multiple. That's what you do. All your college life you'll deal 6 subjects simultaneously in every semester. But at least okay, in the GATE preparation starting, you can start with maths. Okay. So I mixed with mechanics, dharma and maths now, sir. Dharma is like a basic subject. You can start. No issue. Fine then. Okay. Any questions to be asked? Or things are fine, then it's okay. Fine then, thank you all. Okay, yeah, good night all of you. We'll meet tomorrow at 7 p.m. sharp.